Looks like we can start. Welcome back, everyone. So we're midway through week 7, and we only really just started Unit 4B. We took a look into what simple interest is all about. We did a big comparison example where we discussed how simple interest transitions into the landscape of compound interest. We're about to start our really first big compound interest formula, working through the formulas with the calculator. So the calculator is really kind of the big emphasis on both of these units, 4B and 4D. We'll be practicing with it really carefully when we're doing it in class. And that will get you a lot of help and support when you're doing this, say, as a MyLab problem. MyLab can be kind of punishing because of rounding errors. We can't round intermediate computations whatsoever. And because of that, it's highly recommended you have a calculator, say, something along the lines of this one. Doesn't have to be this exact model. It could be a Casio calculator instead or otherwise. But what you want is something where you can type in multiple values, an entire expression in one go, and hit enter. That way we're not worried about intermediate rounding errors that can crop up and lose the whole problem if we were doing it as, say, a MyLab exercise. But after we get through with the compound interest problems in 4B, we have a shorter looking section, but it's actually kind of just as long, using a different formula showing how many months or what your payments might be to pay off, say, mortgages, credit card payments, and car loans, and so on. That's going to finish off the entirety of our chapter 4 before we turn into topics on statistics in chapter 5. But that's where we're at so far, folks. Any questions or comments at all today to start us out? Okay, here's where we left off then on Monday's class. Let me make sure the windows are going to fit just right first. Okay, that looks about right. So I have the calculator that I'm going to kind of demonstrate where all the important keys and keystrokes are going to be. Then Desmos up at top is what we're going to use to just get a fast value out. And I lost the ability to move it once I put it there. Hang on, let me move that down. I'll have Desmos here is also just for a quick reference on values that we're going to get. And this is the big formula that we were looking into before we end class last time. It says the compound interest for the accumulated balance, which we'll call A or amount, after the term of the loan, Y years, is going to be the principal amount, the starting amount that we've invested, or the starting amount that we took a loan on, then times 1 plus the annual percentage rate as a decimal number, raised to the term of the loan in years. So putting that all together, we can calculate, say, a problem like this one in a really, really fast way. We don't necessarily have to build out the table. We can just put in this expression like we did when we were exploring this table to calculate a present value or a total amount after 6 years, like we see in this row. So that's the big formula. We're going to extend on it a little bit to include compounding not just every year, but potentially compounding on the month or even on the day and so on. Well, we took a quick look at this problem. It's all about mutual funds, and we define it down below. It's kind of just our warm-up problem starting out, thinking about these. It says we got a really large tax return, $4,000. We're investing it into a mutual fund, which is expected to earn an average APR of 6%. This was going to be compounded annually, so just once per year. And assuming that we really get that 6% as the average in 10 years, let's say 6% exactly on every single year on those 10 years, we can say determine what the amount to the accounts will be in 10 years, assuming no withdrawals. So here's how we'll go at it. Really, we're just going to drop down the information in the formula as we extracted it out of the problem. So the amount A is going to be first principal amount, $4,000. Multiply that by 1 plus the APR 0.06. And it might look kind of funny on paper how we're always just saying 1 plus 0.06. rather than a 1.06, because 1.06 is just fine. Well, one of the reasons I'm going to leave it like this is because in later formulas, we divide by something here, then one number of times we compound. And if we add these up, we could make a order of operations kind of error on accident in the case we have some division right here. So best practice is usually, just so we don't make an order of operations mistake, just leave it like that, thinking ahead to the new formulas. So we're at this level here, we want to know the value of the account in 10 years. So we just raise this whole thing to the exponent, or we can say the power of 10. So all we need now is a value. Again, this is where it gets a little bit dicey on the calculator if you're doing this kind of work for the very first time. So part of our goal here in these notes is to also just practice what this would look like. If you're punching this into the calculator, like we discussed last class, the major keystrokes we want to be looking into are going to be, for the exponent, it's going to be this one right here. Again, if you have a different calculator, it's probably something like that. But if you're not sure, don't hesitate to take a picture of your calculator, send it to me on an email, and I'll be happy to show how it goes on your calculator. Next thing we're going to need is both the open and close parentheses to organize what goes inside the function, this portion right here, and then just the ordinary operations, typing all this out. So if we were putting this into the TI-30 X2S, it would look about like this. 4,000, you would have to hit the open parenthesis to put in the 1 plus 0.06, or 0.06 would be just fine. Saves on the horizontal space because this is going to look a lot bigger than how I'm writing it down. You can use a left arrow and right arrow to scroll through the input you put in there, make sure everything's right. Then we absolutely have to close that parenthesis. To get the exponent, hit that up arrow thing right there. This will be raised to power. Punch in just 10 years. So it should look about like that when you go to work this out in the calculator. We'll use this one just for a fast way to get a number in class, but the bad thing about Desmos is it doesn't format it the way you really see it in the calculator below. So if you use Desmos a lot to calculate in the MyLab homework, usually it's not a big deal, but I would say for this one section 4B and the next section 4C, it's a very good idea to practice in your calculator because it really feels different what you punch in here versus what you might do with any online calculator, really. In this calculator, it's kind of cleaner and nice to write. It goes 4,000, 1 plus 0.06 to power 10, and everything's just kind of formatted cleanly about how you'd write it on paper even. And this is the value we'd get. I've got $7,163.39. And these problems, as you might notice, have the potential to be really actually kind of fast. I think some of the other work we've been doing in prior sections, even 4A, had much trickier problems. But once you're familiar with how the formula goes, how to throw it into the calculator after extracting the information, that's it. The whole answer is $7,163.39. Well, how's it going for folks with the calculator practice? Anyone getting anything different on their calculator so far? Okay, well, let's try it out again. Here's our next example 4. Example 4 is interesting because this is some real information about a savings account at a real bank, Wells Fargo. This bank is kind of fun to pick on because they were in the news quite a while ago at this point for doing some fraud with their memberships, signing them up for accounts and products that they had no idea that they were a part of. But here's what's going on in this problem. Let's suppose you do have a Wells Fargo's account and you have an amount of $10,000 that's going to be invested. So that's the principal amount that's being indicated here. Organizing the information, we can start by saying the principal is $10,000. That's a lot of money to trust Wells Fargo's with. It's going to be invested for a term of 30 years. So I'll put that 30 years. Maybe not the next thing I want to put down. I would probably put it over here because it reminds me how the information comes together in the actual formula. So just thinking in terms of plugging it in, let's write y equals 30 years, but clear over here. And this is being invested into a Platinum Savings Wells Fargo account. I guess that's redundant. Platinum Savings Wells Fargo savings account. Could have deleted that word right there. And this one compounds annually, so once per year as well. So this account has a $12 monthly fee, so it doesn't sound like the best savings account. Most savings accounts don't have monthly fees typically, but we're told it's waived if you maintain a minimum daily balance of $3,500 into that savings account. So we're not in trouble on the monthly fee. We're investing, again, a huge chunk of change, $10,000. But here's the crazy part. This account, even though its name sounds like it's fancy and we're going to get some high yields, this account earns an AP annual percentage. Oh, hang on, that was a typo there. I meant to say APR, not annual percentage yield. Let me just highlight that all in red. Sorry for folks on that distraction there. This earns an annual percentage rate, not APY, of 0.05%. And that's considered high in the banking world for a checking account, savings account combination. So that's our APR there. APR equals 0. Recall, we have to write this in as a decimal. So much like the 6% turned into 0.06, we have to shift the decimal place that's there by the red dot left 2 more places. So it's 0.0005. So that's our APR on this account. And unfortunately, this isn't unusual. Something happened in the banking world after around year 2000. The interest rates on savings accounts just took a nosedive. I think other things like the financial crisis of 2009 just kept them down. And so that's, although abysmal, a pretty realistic amount. We're told next, the savings account is linked. If we get this 5% APR, if the savings account is linked to a premium Wells Fargo's checking account, and if it's not, it actually earns 1% APR. So quite a lot worse, actually, but still close to zero in either way you look at it. So it's kind of interesting to look into this information because it sounds like it's a nice savings account. But if we're investing into any kind of savings account about like this, we're not going to earn a lot of interest. We're saying, assuming we make no withdrawals on that 10,000 initial deposit, what is the value of the account after the term of 30 years? I guess that was already indicated above. This problem had an interest rate of 6%, and we earned quite a lot in interest. There's a principal, but after 10 years, we're at 7,000. So we've earned $3,163 and some change in interest. But it's going to be kind of shocking when we see what happens with this one after 30 years with a pretty high principal. So let's reset this here. Next thing we should do is throw it into the formula. The formula isn't quite there. We scrolled past it, but this is a pretty good skill for just getting used to working with this formula. If you write out on paper, A equals P, 1 plus APR raised to the power of Y. We've duplicated the formula above in the notes, and this really helps us get started on knowing what is going to go where. It's going to kind of just leak into your subconscious the more and more you write down that formula, even though you can just put this on a page of notes for exam 2. This is a really good strategy just for getting used to working with it. In fact, if this was an exam problem and you put this on paper, but maybe something went wrong, you ran out of time, but I saw that, that's worth some partial credit. It would indicate to me that you know what formula is relevant to this problem. If this was a 5-point problem, it's probably 1 point partial credit. Not a whole lot, but it's worth something for sure. Next, with the formula down, we just take the information we extracted from the context, put 10,000 in place of the principal, 1 plus that 0.0005 for the APR, raise it to the power 30 years. And even though exam 2 is kind of far away, it's good to think about if this was a real exam question, how would it be graded? The trickiest part for sure is putting this in the calculator and getting the number out. But this is a good amount of work right here already. And if this was a 5-point problem, I would say that this would be 4 points out of 5 for partial credit. On exams. So if you show me on paper what you've got before you put it into the calculator, and everything here is just right, this is written as an exponent, you've got the right APR and so on, then I would give a lot of partial credit for just that step right there. This makes it so it's less of an anxiety thing of accidentally just having a big thumb and hitting the wrong button. Even if you put everything in perfectly, if you put in the wrong number of zeros, we get the wrong answer. I'm testing more on the concept and not trying to give a ton of emphasis on just the calculator work. It's still important. If we get that step wrong, we're not going to get it right in my lab whatsoever. And 1 point is still sometimes a good amount on an exam. Every point matters. So the major reason for this is it kind of sucks to have a problem where I'm grading the exam, you've got a number down, and there's no way for me to tell how you got that number. In that case, we lose all the basis for the partial credit. And so this is my way and encouragement. Write this down on paper. You're probably going to get some good practice thinking about how the formula goes. It'll be more accurate with the calculator if you have it on paper first as well. And then it gives me the basis for partial credit at the same time. So let's throw this in. Over here, if I put this in, it'd come out as, here's the 10,000, 1 plus 0.00030 zeros and the 5 to power 30. And this is what we've earned in 30 years. This is kind of crazy in a certain sense. $151.09. Well, we add the principal amounts to it, so the total value of the count is $10,151.09. Well, is that all right to folks? Any questions on getting that so far? Okay, again, if you were plugging this into the calculator, these are the major keystrokes you would have to work with. And this is what it would look like written in, say, a calculator format. So for the calculator, it would look something about like this, 10,000. Definitely don't put a comma in, even though I think there is a comma on this calculator. Maybe not this one. Some of them do have commas, but that's going to throw it off. That might have a different meaning. Then a parenthesis will automatically indicate multiplication. 1 plus, usually I just go point, then 0.005. Then the exponent key, and 30 is all what your calculator would look like. You might be able to see it in one screen depending on the model. On this one, you'd have to scroll left and right to see the whole thing. Well, we did it, folks. Again, Wells Fargo, even though we're kind of picking on them in this problem, isn't unique. Savings accounts for banks and credit unions are also at the very, very low end. 0.01%, 0.05% are typical values. Well, this was supposed to be the power of compound interest or power of compounding. This didn't seem too powerful at all, just getting $151 in interest. But if that interest rate was just a little bit better, say, bump it up to a 6 here, that's not a whole lot. We're now at $181, so we only earned about $30 by going from a 0.005 to a 0.006. But what if it was 6%? You would delete and make it a 0.06, And now that's some real growth. We started with 10,000, we're at 57,434 and some change. So if the interest rate is just a little bit better, say 6%, and some situations can be even higher than that, although there's risk associated with it, suddenly after 30 years, that's a decent amount. We're not going to retire on that, so we have to deposit more and more money, not just at the original 10,000. But imagine it was even better, say 9%. We have now gotten $132,000. This is starting to grow kind of explosively as the interest rate increases. But it's not just about the interest rate. This is a true exponential growth. And so we see the value just take off after enough time goes by. If we say invested for 35 years, no withdrawals, we're at 200,000. Go to 40 years, we've hit 300,000. We might be starting to get on in our years at that point. So that's the sad part about it. Go up to 50 years and we're close to 750,000. At 60 years, we've exceeded 1,000,000. We're getting closer to 2 million. That's a humongous change, just adding 10 years. 30 to 40 years might have not looked impressive, but 50 to 60 years, suddenly that's a humongous amount we're earning. Increase to 70 years, and again, we're probably very long in the tooth at this point. We're hopefully retired, but now we're beyond 4 million. And we kind of get the point. This is what they're trying to emphasize with the power of compound interest. This is true exponential growth. We just have to let enough time go by. Even with a bad interest rate, if enough time goes by, this 10,000 principal starts to just take off. But this is going to be like 150 years or 200 years where it starts to look like these kinds of values. Well, this is all about annual compounding so far. What we're going to turn into next is what happens when we compound n times per year. If we say semi-annually, we mean twice a year. If we say quarterly, we mean 4 times a year. And often I'll define that in the problem, so we're not guessing in, say, an exam situation. The formula is pretty similar, except we make a change here. We divide by the APR, by the number of compoundings. And if we're compounding n times per year, we don't just put the term length here. We take n times the term length and write it in as the exponent. So that's our new formula. Let's blow it up a little bit. It has a very similar format. The principal goes here. APR goes here. Term length is in this spot. And we just have to find out how many times we're compounding to get the value n, to plug in those two new spots. Well, this is the one and only one new thing about this, the number of times we're compounding per year. Any questions about the formula so far? Okay, let's give this a try then. Here's just a fast example where we can focus just on the elements of the formula, not get bogged down on weird elements of the context, like in the next example. It says for this scenario, you are saving for a dream vacation in Sri Lanka. Make sure you know the laws before you go there because you can get in all sorts of surprising legal trouble. It's an interesting place, regardless. So for this dream vacation, you've got $9,500 we're investing into a mutual fund, which is wise because the Wells Fargo's Platinum Savings account, no matter how many bells and whistles they put on it, isn't going to earn us any money. But a mutual fund, even at a 4.5% average APR, that's going to get us some real growth on that account. So we have this much as the principal amount we're going to invest, the starting principal. P equals 9,500. This is a mutual fund, which means the true APR is going to vary year by year. For the sake of a math problem, we're going to say it has an average 4.5% APR over the term, and soon further, that's going to be exactly 4.5% for each one of those years. So this is really going to be just an estimate altogether, but we'll see about what it'll turn into. So next we have APR Just like with all the formulas, don't forget to convert that APR into a decimal. So if it's 4.5%, take the decimal point that's right here and scoot it back 2 places. So 0.045 is our APR on that. Let's reuse that same emphasis as we did before. That's one of the easier mistakes to make. But we've got our APR down. It says compounded monthly. And so this is the number of compoundings that we're interested in. Let's use that same color coding there. If it's compounded monthly, it's just saying the number of times per year is going to be 12 on this one. And the term of this investment will be 10 years. So that's going to be the value for Y. So we just about to have all the information. And again, when you get really good practice on these, when you're doing them, say in MyLab, it's tempting to just punch this all into the calculator as you go. But it's dangerous in an exam setting to just punch all this and put down a number as your whole answer. Because if we make any mistake anywhere, say a decimal point here, forgetting that, say, n is 12 or the term length, maybe we just make the smallest mistake anywhere, all basis for partial credit is lost, making it a tricky problem in that sense. But we've got the formula there, so let's write in, if this is on paper on the exam, this is the protection, the insurance against losing a whole bunch of credit. This will be 4 points if it's written in through the formula, 4 points out of 5, exactly right. So I'll put in 9,500 to start. Now we have 1 plus the APR. So 1 plus 0.045. We also have to divide immediately at that step by the number of compoundings, so 12 in this problem for n, and we raise it to 12 times the term length. So 12 times 10 years. So that's the total evaluation of the formula. Next challenge is getting all of that in the calculator. So it's going to be stuff like we saw here. We'll have a division in this spot. And we have to be really careful with how we write in that exponent. So let's put this on paper, what it would look like in the calculator first. And then we'll compare our answers as I compute it in Desmos. So if I'm punching this into a calculator like this, the highlighted keys are still the major relevant ones. And it would go like this. Well, there wouldn't be a dollar sign, so let me start over there. 9,500. Hit the parenthesis sign, 1 plus 0.045. Hit the division key here, and let me just double check I know what that looks like. I'm pretty sure it's just a slash. Okay, so division, it's going to look like this, division by 12. But now we have to be really careful with what's going on in the exponent. On paper, it might not be a bad idea to put parentheses around those, just as an emphasis. There's kind of two schools of thought. You could just say power is 120, certainly, 12 times 10. But if the numbers are really large and you just wanted to put that in the calculator in one shot, be extra careful here. It's going to be raised to the power of, new set of parentheses, 12 times 10. So if you put it in your calculator just like that, you'll be in great shape. So back to this calculator. It'll be 9,500, 1 plus 0.045, divide by 12, raised to the power of 12 times 10, or 120 is just fine again. It's telling us after 10 years have gone by, we now have, for our dream vacation, we did grow a whole bunch, but it was only 10 years, and the APR was kind of low, but now we've got to almost $15,000. So maybe we won't have to use the credit card as hard. We can have a great time in Sri Lanka. So we'll say here, the amount comes out to be $14,886.43. If you did this in an exam and you're feeling supremely confident on your calculator skills, and this is the whole thing you put on paper, it is for full credit. But again, we're really emphasizing these steps here just in case anything goes wrong. Forgetting a parenthesis here and that spot can make it all go wrong, or just forgetting it's not 10, it's 12 times 10 for 120 will give us a totally different value. Well, any questions at all, folks, on getting that number? Okay, another thing I want to discuss, mostly as it pertains to the MyLab homework system, is MyLab is going to be really kind of brutal on these numbers. They want accuracy to the nearest cent, which is kind of rough in a certain sense. I mean, if this was an exam problem and you said $1,400, $14,000, 886, and say 75 cents, I would say, oh, there's probably a rounding in the middle. You understand the concept, the formula, you put in the calculator right, you just round it somewhere. And I'm not too picky about that. But MyLab is. So here's the one thing to watch out for. A different way to do this kind of computation, instead of writing it in as one whole line, is thinking in terms of order of operations. Sometimes people prefer to go this route. Take 1 plus 0.045, divide by 12, and let's say, well, let's keep it just like that. If we take that, then we can just write down that number on paper, put it in here. Then the next thing you might put in the calculator is 1.00375 to power 12 times 10, so 120. And we have that number down. So we have done the thing on the inside, following order of operations. Next step in order of operations is the exponent. So we raise the thing on the x inside to the exponent. And the final step is to multiply. So we'll take 9,500, multiply it by 1.567, say. And that doesn't seem too unreasonable, right? We rounded to the nearest thousand, 3 decimal places. But if we do that, we get $14,886.50. MyLab is going to say, hang on, that's supposed to be 43 cents. We are 7 cents high, and that matters to MyLab. So if you do decide to go this route, my advice is capture possibly just all of the decimal places, or maybe about 8 of them at minimum. Depending on the problem, you'd be surprised at how many decimal places really matter, especially if a division comes up, like in the next section. So if we go 1.5669, we're still not there. We're at 55 cents. Let's go 9 again. Now we're down to 40 cents. 2. We're getting close, and we're all the way up to that decimal point. So this shows us how much rounding in the middle for this computation really matters. So go 7, 7. And once I went to, let's put in just the first 7. Once I went up to that decimal place, 1, 2, 3, 4, 5, 6, 7, 8 decimal places altogether, finally our answer agrees with what we did originally, to the nearest cent at least. So that's a warning. If you are doing everything right, really, but you feel like you're getting all of your answers wrong in MyLab, it's possibly because rounding too much in the middle. MyLab is going to get really upset if we round like this and say it's 14,915. Well, it's about money, right? So money matters. Every cent counts in the world of accounting and banking. There's multiple ways to do these. So if you go with order of operations, capture as many decimal places as your calculator gives, just for the extra assurance you have the right value. Boom. We have a couple more problems along these lines to practice. Any last questions at all, folks, before we try the next? Okay, here's the next scenario we're going to take a look into. For this one, it says, you deposit 12,500 from an inheritance. Lucky you. I mean, that's maybe not completely lucky. Sometimes it means someone might have passed away, but you've got $12,500 and you're going to deposit it into a certificate of deposit or CD account to save for a home renovation. The CD has a term of 7 years. APR is reasonable, not like the Wells Fargo's Platinum Savings account. This one's at 5.2%, compounded quarterly, 4 times a year. And just for a quick definition, CD accounts are considered illiquid in the sense that it is very difficult to access funds until the very end of the term. So we're trying to give almost a guarantee to the bank. We're not going to touch that money. They're free to do whatever they do with it, invest it somewhere, essentially trying to make more money than what they've lent assured us from their APR. We need to compute the final balance after the term ends. But this is a kind of a weird word. Let's pause right here for just a moment. When we say illiquid, what we mean is liquidity is the ease at which money is accessed. So a savings account, say at Wells Fargo, is highly liquid. At any point, you can log into Wells Fargo, move from savings into your checking, and you've liquidated that amount of the savings account. CD accounts are illiquid, and if you try to take some of this money in, say, year two, it might be possible, but there could be a huge penalty. They're going to charge you to do that. Who knows if they'll allow you to do it at all? It's going to be up to the terms of the bank itself. So that's what makes it illiquid. And if, say, we're talking about a company that goes totally bankrupt and they have to sell all their assets, we say that we've liquidated the company. So liquid and money seem to have a weird symbiosis in the English language. Well, let's try this one out. I think this will be a good one for the class to try. I'll get quiet for the next, say, I think 4 minutes is good for this one. So give this one a try, come up with the amount of money at the end of the term, and we'll compare our notes at, say, 641. Yep, that looks right, Echo. Thank you. Awesome, Caitlin. Yeah, if you can get to that number, I'd say you're in great shape for getting through the MyLab homework. It's not going to be too much of a pain, and the exam questions are about like this as well for this unit. Okay, thanks for practicing this one, folks. And yeah, thanks for also putting the numbers out in the chat. I agree, I've tried it out myself and I got the value 17,946 rather, and every cent matters, 28 cents. Anyone get any different value? Any questions on putting it in the calculator for this one? Okay, well, just for the sake of completing the notes, this is what it would look like, say, doing it as an exam question, putting it down on paper, put 12,500, multiply against the group, 1 plus APR is going to be 0.052. But then we divide by the number of times we're compounding. Quarterly indicates 4 times per year, so divide by 4. Then we take 4 times the term length, which is 7 on this one. So on paper, this is what it would look like. In a calculator, it would look more like this, though, with the appropriate values to match this particular problem. But we got through it, folks. Next problem, it looks like it's pretty similar, but then we're going to change gears just a little bit and swap, which is unknown. A has been the unknown so far. We can swap that with the principal P, but let's practice one more problem and just to see how it goes, and we'll try the last two kind of challenge questions for the notes. Well, on example 7, in a certain sense, in the sense of liquidity, it's the opposite of example 6. CD accounts have typically decent APRs, but if you want an account that is not illiquid, if you want a liquid account, the one you can grab your money from a little bit more fast, and you want to earn some interest on it, it would be an account typically called a money market account. They're highly liquid in the sense that you can transfer your money. It is a process. It's not like going into your Wells Fargo account, moving it from savings to checking. It is a little bit more of a chore, but that's good if you want to have this money as being kind of an emergency fund. It is highly liquid compared to a CD, but it takes sometimes a good amount of steps to actually get that money. So you have to really want it, but you can get it when you need it. The story of this problem says you place, it looks like a tax refund again, a tax refund of 4,500 into a high yield money market account. So that's our principal amount. To serve as your emergency fund, we're told that these accounts are highly liquid, easy to cash out, and the account offers an APR of 3.5%. I think that is kind of high actually for a money market account, but assuming we get that interest rate, that was the stuff you could have gotten, say, in the 80s back in the day. You'll have daily compounding. That's kind of surprising. And maybe a little exciting. You can check your account every single day and see how it changes. Not by much, but you can do that. Compute the balance in the account after 25 years of growth. I add a little bit more to this. This is an emergency fund. So realistically, we're going to probably take money out. A water heater is going to break. A car is going to need repairs. The cat might have to go to the vet. But if we make the assumption that we don't touch this account, there's been no emergencies, we'll find the balance after 25 years, quite a long time. Almost would imply maybe we forgot we had the account in the first place. It's the same kind of idea as before. We run it through this formula that we see. But we found that the principal going in the first slot is 4,500. Doing a little bit of organization and bookkeeping is well worth the effort on this. APR is 3.5%, so write that in as APR 0.035. When it says daily compounding right here, we mean the end value in the formula is 365. And we have a term of y equals 25 years. So those are all the moving parts. Input them into the formula, and here's what we're going to get. The amount A is going to be first the principal amount, 4,500, multiply it by the group, 1 plus from this level, APR, 0.035, division by the number of compoundings per year, so now 365, raise it to the 365 times the term length of 25 years. I think the easiest mistake to make on this one, once we get a lot of good practice, is if you're putting this in the calculator, I think a lot of people just put in a 28, and that's a good call. But this one's a little bit more annoying. The numbers are kind of inconvenient. Just make sure when you put that in the calculator, you wrap it around another set of parentheses. So this one in the calculator comes out as, oh, hang on. Firefox always wants to update, it seems like. This one's going to come out as 4,500, 1 plus 0.035 daily compounding. So divide by 365, raised to power 365 times 25. And here's what we get. $10,794.49. That's pretty good for emergency fund on a kind of a low yield account comparative to other accounts we've looked into. But it was 25 years, so that did take some time to get to that level. But the amount is $10,794 and 49 cents altogether. Well, any questions at all, folks, finding that value? Any questions with the calculator in particular? Okay, well, daily compounding, again, it looks really impressive. Your value can change every single day, but it's possibly changing in maybe a cent or tenth of a cent or hundredth of a cent. So it might actually look the same on a day-by-day basis until it changes, depending on the balance and the interest rate. But one thing to compare this against is if we put a 1 there and a 1 there, this is just the annual compounding formula. You'd have the APR when you divide, 1 times 25 is just 25, and compare the difference. We compound just once a year for 25 years, it's $10,634, whereas here it was $10,794. There's absolutely a difference there, but it's not as spectacular as we might have thought. If we do it monthly, then it shoots up to 10,781. And now it's really close. It's only different in the tens of dollars at this point. If we compound, say, twice a month, that'd be 24 times per year. We're looking at $10,788.06, getting even closer to that value. So jumping this up to 365 days, although impressive and kind of interesting, really not a whole lot different than, say, monthly, but every cent and dollar counts, so it did give us a little bit more. If we did something kind of ridiculous and say compound, how about 365 100,000 times a year, it's still not much off. It's didn't even gain an extra dollar. So there's kind of a limiting value to this process. The more you compound, the more you're earning per year, but the amount extra you're getting by increasing the number of compoundings, it has very, very diminishing returns. So it becomes less and less oppressive as you just add more and more compoundings to it. The only way to really get more out of this is if we're willing to have an account that is not very liquid at all, say a money market fund, maybe it's a retirement account of some kind, the interest rate is going to jump more likely. And if we have a nice retirement account, maybe we're at, say, 7.5%. Change to a higher interest, giving up liquidity, means our value has gone up by a lot. And that's kind of impressive. If it's, say, 70%, double that APR, then the amount we get here over 25 years is more than twice this amount. So doubling the APR doesn't necessarily say you're doubling the amount. The amount of time is a big factor there as well. Well, these are the major routine problems that you're going to see in the MyLab homework, but there's a couple more we're going to take a look into. So far, I'd say examples 3 through 7 are going to be the major ones you can expect for an exam situation. But examples 8 and 9 are interesting in their own right. There's a couple just like these in the homework. So we'll practice these out as well. These go a little bit differently. It says, you want to help your child open a restaurant in the future. How much must be deposited today into an account with semi-annual compounding, so twice a year, with a nice APR, so maybe this is a CD or some money market fund, or mutual fund rather, in order to have $60,000 in 3 years. So this one's interesting because we think of the principal as being the present value, the amount here as the future value. So here's the future value in 25 years. The principal is the amount you have, the present value, the amount you're about to deposit because you just got that tax refund. So that's the present value. But this question is asking, what is the present value to get a future value, 60,000 in 13 years? So future value. That's the unknown in this problem. So it's kind of like it just threw this formula kind of on its head in a certain sense. So we do not know the principal. Principal is a complete unknown on this one. We know the future value amount. This amount A being 60,000, this time is the known. We've got a figure of 60,000 altogether. And what else do we know? There's a, let's see, an APR of 5.5%. As a decimal, it's then 0.055. We have compounding being semi-annually, twice a year. Tells us in the formula that we're going to use, the n value is 2. And we happen to know the term length, y is going to be 13 years. So it becomes a tricky problem. You know, one thought is you could put things into a formula like this, make some adjustments, put in a, say, 2 here, 2 here, change what the APR is, put in 0.055 now, and just try to put in the right value that's going to target $60,000. So 9,000 didn't get us there, so maybe 13,000. And you know, this approach, it absolutely will work, but it's tedious, and we've got to get this down to the exact cent of $60,000. If you have the patience, it will work. And I would say there's no harm thinking of it in those terms. But let's do it a totally different way. Let's put down the formula for compound interest, compounding twice a year. Formula goes amount equals principal 1 plus the annual percentage rate, APR, divide by n raised to the power, n times y. So there's our whole formula there. And because we don't know the value of P, but we know the value of A, we can transfer this into the new formula. So here's the formula. For a present value, P, unknown. That's why we have P as a question mark. It's the unknown in this situation. And the formula is not too bad. If P is the unknown, you divide by this whole entire thing. So here's the next formula. P equals amount A divided by 1 plus APR divided by N raised to power N times Y. So that's our brand new formula. If we plug in all the information that we have, we do know the future value, A, is that $60,000 there, also written over here. We'll get the present value we need to invest so that the child can open up that restaurant with the $60,000. Hopefully, when we came up with that money, we were thinking in terms of inflation, what we expect it could be, so that in $13,000, the $60,000 is still impressive for getting started. Well, any questions at all about the formula so far? Okay, next thing we'll do is just plug in the information. The major challenge again is really just navigating through the calculator. Once we have the formula, we read through the context and we know what all the other values are, we're just plugging them in. So 60,000 goes up into the numerator. Then go down to the denominator, 1 plus APR, which we've written down as 0.055. This is going to be compounded twice a year in whichever account this might be. So divide by 2, then raised to a power of 2 times the term length of 13 years. So I guess we're expecting the child is going to graduate from culinary school somewhere in 13 years, and this will be their startup fund. Okay, now we've got to put that into a calculator. First, I'll show how it goes on Desmos. Try it out on your own. Then we'll write it down on paper what the calculator input is going to look like. So take 60,000. We have a complicated looking denominator, so divide by 1 plus 0.055 divided by 2 to the power of 2 times 13, or just a 26. Means you wouldn't have to put in those parentheses, slightly nicer to put in. So throwing all of that into the calculator just right, and it's, again, tricky. It's differently tricky from the other problems. We get a principal of $29,636. Let's round to the nearest cent. 28 cents must be deposited today. Unless we're thinking of a payment plan where we're going to deposit a little bit every single month over the course of 13 years, there's some pretty good formulas for that. That's going to be unit 4C, but because those formulas get kind of wild and unexpected, we're going to skip over to unit 4D, the opposite end of making payments. But any questions at all, folks, on the 29,636 principal? Okay, and again, if you were throwing it into a calculator, say something like this one, here's about what it would look like. Start with the 60,000, no commas. 63 zeros after that. Then immediately just punch the division key. And you're absolutely going to need parentheses, but we expected that. Parentheses were needed with both versions of this formula, the original one and this one for principal. That's going to be 1 plus 0.55, rather 0.055. Divide this by 2, and then raise to power. I'm running out of space, so I'm going to just write this in as 26. So putting in the calculator just like that should give you this kind of output. Well, we did it, folks. We can now determine the amount to deposit today to target a specific future value. So if we want, say, some different amount, if we feel like this kid worked really hard, they're our favorites, we want to make sure they start off strong and they need to have $1 million, we could just put in $1 million to start off. They're going to buy a building, maybe that's the thought. You need to invest almost $500,000 today over the term of 13 years. So these are kind of fun formulas to play around with. Change the interest rate, change the future value you're going for, or the term length, just to see what happens. Yeah, that would absolutely be the case. For some reason, maybe they're the last child or the first child, who knows? They're going to get a big help. Or maybe that child just was cooking every day and they deserve it. The parent is thinking, who knows? Well, any questions or comments at all, folks, on example 8? Okay, well, with this nice handy formula right here, let's try this out again on example 9. I want to kind of just convey that that's the answer because I circled something, and that's just the formula that we are using to get through the problem. This one says you're planning ahead for your child's education. So pretty much the same sort of situation. Maybe this is a different child. One of them is going to open a restaurant. Another one is maybe just going to, we're not sure, but we're going to fund their education. We'll figure it out along the way. How much must be deposited today into a mutual fund this time? This one has quarterly compounding. And I want to add to the notes, if this was an exam question, I would write 4 times per year. Let me just throw that in as a quick edit. APR is going to be 6.4% on this one. So a little bit more competitive than the last problem. And we want to have an amount A, future value, of $400,000. It sounds like a lot, but this is, again, in 18 years. So that might not be as much as we expect, depending on inflation, the ever-rising cost of college, which seems to outpace inflation by quite a lot. So this person's really thinking ahead. To get this value, really, it's just a matter of navigating the equation one more time. Let's give it a try. Put in principal is going to be equal to, in the numerator, the amount A, that's the future value. It's $400,000 on this one. Then we just move on to the next line, or next level, denominator, 1 plus the APR. But always remember, convert it to a decimal. We can get some pretty weird numbers otherwise, but you'll usually be able to spot them. The numbers just don't seem to make sense if we put in a 6.4. 0.064 gives us that percentage. But because we're compounding 4 times a year, we divide that by 4. Then we raise this to the power of 4 times 18. So throw this into the calculator, and we'll have a value for this one now. In this calculator here, this is what it would look like. 400,000, 1 plus 0.064, divide by 4, to power 4 times 18, and definitely use parentheses on that exponent, unless you multiply the numbers together. We're being told, well, it was a term of 18 years, slightly higher interest rate, so getting to $400,000 maybe wasn't as much as you might expect. It's still a lot of money for sure. $127,000, 559. And 56 cents. Keep in mind, though, it's a mutual fund, so we also made a pretty big assumption on this one. It's not a CD certificate with a guaranteed interest rate, APR. This one is going to fluctuate. We might have looked at a prospectus that told us over the years it had an average APR of 6.4%. But it could be some really bad years going forward for 18 years. The APR could be really, really low. We might find that we never got to 400,000. So the strategy for the other child on example 9 through the mutual fund is risky. But if it pans out, then this was not too much to invest. We never said what this account was, so this one might have been a risky account as well. That looks kind of high for a CD. Well, any last questions at all, folks, on either one of these type of problems? Okay, again, the next section we're going to cover in section 4D is going to be along the lines of maybe we have a car loan for, say, $30,000 at a certain interest rate, maybe 5%, something like that, over a term of how about 84 months, those are becoming more popular. We might wonder what would the car payment be on a monthly basis for that to pay off the loan. It kind of extends past the unit that we're skipping, 4C, where 4C is a little bit more of a realistic problem. This parent wants to come up with $400,000. They better have that money right now. And if they're like most parents, that's going to break the bank. They may not have it. The alternative strategy is come up with a monthly investment into this account to get up to 400,000 in 18 years. So that's a unit we're skipping on 4C. It's pretty interesting if you want to take a look into it and read through. The 4D is the opposite end. We're going to look into paying off loans, credit cards, mortgages, car payments, and so on. It all kind of extends for the kind of work we've done here. So if you feel pretty confident working the calculator with what we've done so far, it's not going to be too different, just different set of formulas. Well, any last questions or comments at all, folks, before we call it a night? A little bit early again today. Okay, well, have a great night, folks. On Thursday, we'll switch gears into paying off things and see how that goes. Come ready with your calculator, and if anything comes up, if any questions or weird results come out, don't hesitate to ask. I'm very happy to spend the extra time just showing how it works through the calculator. That'll make the MyLab process a lot less painful. But have a great night, folks. I'll see you all Thursday. Thanks. Have a good one.